The telescope that showed us the edge of the universe has one blind spot, and it sits right above our own ocean. Every time Hubble crosses the South Atlantic, it shuts its most sensitive eyes on purpose, because there is a growing hole in the Earth's magnetic shield there, a place where space itself leaks too close to the ground. That hole is spreading by an area near half the size of Europe in a single decade, and it has just begun to split in two. It is one symptom of a shield weakening across the entire planet, driven by a churning core we cannot see and cannot fully predict. So the real question is no longer whether the field is changing, it is what happens to us if it keeps going. If you want the honest answer, not the panic and not the hand-waving, subscribe to the Sky Lab, because that is exactly what we do here. Drop a comment and tell me where you are watching from, and whether this makes you look up at the sky a little differently tonight. Now, let's get into it. Part 1. The place where the shield runs thin. Somewhere over the South Atlantic right now a satellite is going quiet. It isn't broken, it isn't falling, it is holding its breath on purpose. The most sensitive instruments on board have been switched off by the people who fly it, because the spacecraft has just crossed an invisible boundary in the sky, a place where the thing that normally protects it thins out to almost nothing. The engineers who operate these machines have a grim little nickname for the zone underneath them. They call it the Bermuda Triangle of space. That name is a joke with something serious hiding behind it. There is nothing supernatural over the South Atlantic. What there is instead is a genuine weak spot in the magnetic field of the entire planet, a dent, a soft place in the armour. And over that soft place, the radiation that fills near-Earth space presses closer to the ground than it does anywhere else in the world. Satellites that pass through it get their memory scrambled, their electronics glitch. Now and then, one of them takes real damage. The Hubble Space Telescope, one of the most valuable eyes humanity has ever built, simply refuses to look while it is inside this region. It closes down its detectors and waits until it is out the other side. I want you to sit with that for a second, because it is the whole story in miniature. There is a spot above the ocean where the shield around our planet has worn so thin that our own machines have to hide from what comes through it. And here is the part that turns a curiosity into something worth 2 hours of your attention. That spot is not staying the same size. It is growing. It is sinking further. And in the last few years, for the first time since we have been able to watch, it has started to split in two. Let me back up and tell you what the shield actually is, because most people go their entire lives without ever thinking about it, and it is the single reason you are alive to be annoyed by that fact. Nearly 2,900 kilometers beneath your feet, far below the crust, far below the solid rock of the mantle, there is an ocean. Not an ocean of water, an ocean of liquid metal, mostly iron with a little nickel mixed in, hot enough to glow, wrapped around a solid inner core the size of the moon. That metal ocean is in constant motion. It rises, it falls, it swirls, and because the Earth is spinning, all of that swirling gets organized into long looping currents. Moving metal carries electric current. An electric current makes a magnetic field. The field makes more current. The current sustains the field, and the whole thing feeds on itself in a loop that has been running, more or less, for billions of years. Scientists call this engine the geodynamo. You can just think of it as the beating core that keeps the lights on. The field it throws off does not stop at the surface. It keeps going, out past the clouds, out past the orbit of the space station, tens of thousands of kilometers into space, forming an enormous invisible cocoon around the whole planet. That cocoon has a name too. It is called the magnetosphere, and it is doing something for you every second of every day that you have never once had to thank it for. It is standing between you and the sun. The sun is not the gentle yellow disk it looks like from a park bench. It is a nuclear furnace that is constantly blowing a wind of charged particles out into space, and every so often it hurls 1 billion tons of that material at us at once. Without a magnetic field, that radiation would slam straight into the top of the atmosphere and over time strip it away, molecule by molecule, into space. We are not guessing about this. We can see exactly what it looks like when a planet loses this protection, because one of our neighbours already did. Mars once had a churning core and a magnetic field of its own. That engine died a long time ago, the shield went with it, and the solar wind spent the next few billion years peeling away the Martian air, until what was left was the thin, cold, dead sky we see today. Mars is the cautionary version of Earth. The difference between the two worlds is, to a large degree the difference between a core that is still alive and a core that went quiet. So the shield matters. That is not an exaggeration, and it is not a scare tactic. It is the load-bearing fact underneath everything else I'm going to tell you. And the reason we are here today is that the shield is measurably, undeniably weakening, and the weakening is happening fastest in that one enormous region over the South Atlantic. Here is how we know. Since the early 1830s, when a German mathematician named Carl Friedrich Gauss first worked out how to measure the strength of the field across the whole globe, we have had real numbers to compare against. And when you line those numbers up across the last century and a half, the trend is not subtle. The overall strength of Earth's main magnetic field has dropped by close to 9%. 9% in under 200 years after billions of years of the engine running. That alone would be interesting, but averages hide the real story, because the loss is not spread out evenly across the planet. It is piled up, concentrated, dug in, over one part of the world. Draw a shape that starts near the bottom of South America, stretches east across the South Atlantic Ocean, and reaches all the way to the coast of southwestern Africa, and you have drawn the outline of the weak spot. That is the South Atlantic anomaly. That is the hole in the shield. Inside that outline, the field is so faint that the inner belt of trapped radiation surrounding our planet, which everywhere else stays comfortably far out in space, sags downward until it is only about 200 kilometers above the surface. 200 kilometers is nothing. That is low enough to reach right into the paths of the satellites we depend on. It is why Hubble hides. It is why the International Space Station carries extra shielding, and why the astronauts on board schedule their spacewalks to avoid crossing this exact patch of sky. The people who live and work in orbit already plan their days around a weakness in the Earth's magnetic field. Most people on the ground have never heard it has a name. And that brings me to the reason this is a story right now, in 2026, and not just a fact in a textbook. For most of human history, we had no way to watch the field change. We had scattered compass readings and a few observatories. We were reading the shield the way you might read a clock by candlelight, catching a glimpse here and there. That is over. Today there are 3 spacecraft launched by the European Space Agency and flying in a careful formation whose entire job is to map the magnetic field of the Earth continuously in fine detail from orbit. The mission is called Swarm, and what Swarm has been showing us year after year is not a shield sitting quietly at 9% below where it used to be. It is a shield in motion. The anomaly is spreading. Since around 2014, it has grown by an area nearly half the size of the entire continent of Europe. In one recent year alone, it expanded by roughly 8%. And the newest, strangest finding of all is that the single weak spot we have been describing is no longer behaving like a single weak spot. It is developing a second center. It is, in the most literal sense the data will allow us to say, beginning to tear into 2. That is the thread I'm going to pull on for the rest of this, not the panic version, where the poles flip on Tuesday and civilization ends by Friday. The real version, which is stranger and more unsettling because it is true. We are the first human beings who have ever been able to watch the Earth's magnetic shield develop a hole and start to split in real time with instruments precise enough to see it move. The question that hangs over every number I am about to give you is deceptively simple. Is this the planet breathing, the way it has breathed for billions of years, in a rhythm too slow for any one lifetime to notice? Or are we watching the first quiet frames of something much larger beginning, without being able to tell the difference until it is already happening to us? Nobody can answer that yet. But to understand why nobody can, you first have to understand how we learn to see the invisible in the first place. Part 2. How to see the invisible. The problem with a magnetic field is that you cannot look at it. You have felt it if you have ever held 2 magnets close and felt them push or pull through empty air, but you have never seen it, because there is nothing there to see. It is a set of instructions written into space itself, telling any charged particle or compass needle which way to go. For almost all of human history, that invisibility meant the field could be changing dramatically right over our heads, and we would have no idea. A medieval sailor with a compass could tell you which way was roughly north. He could not tell you that the north his needle pointed to was slowly walking across the top of the world, or that the strength behind that pull was quietly draining away. Carl Friedrich Gauss changed the first half of that in the 1830s. He was one of the greatest mathematicians who has ever lived, and he turned his attention to the magnetic field with the same ferocity he brought to everything else. He built more sensitive instruments, he organised observatories to take readings on the same schedule around the world, and crucially he developed the mathematics to take all those scattered local measurements and reconstruct the shape and strength of the entire global field from them. For the first time, humanity had a real baseline, a snapshot of the whole shield that future generations could measure themselves against. Almost everything we say today about how much the field has weakened traces back to the fact that Gauss gave us a starting line nearly 2 centuries ago. In fact, our written record of the field reaches back even further than Gauss, in a rougher form, through the logbooks of sailors. For centuries, ships crossing the oceans wrote down the difference between the direction their compass pointed and true north, and those scattered readings let us reconstruct, however crudely, how the field behaved long before anyone could measure its full strength. As far back as the year 1701, the astronomer Edmund Halley, the same Halley whose name rides on the comet, published one of the first charts mapping how compass directions varied across the Atlantic. So the habit of watching the field is older than it first appears. What is new is not that we look, but how sharply we can see. We went from a sailor's compass and a hand-drawn chart to 3 satellites resolving a weak spot, dividing itself in real time, and that leap in precision is exactly why a change earlier generations could never have caught is now impossible for us to miss. But ground stations, no matter how many you build, have a fundamental limit. Most of the planet's surface is ocean, and you cannot easily put a permanent magnetic observatory in the middle of the South Atlantic. For a long time, the very region where the shield was weakest was also one of the hardest places to keep a close eye on. To really watch the field, you had to get above it. You had to go to space. That is what the Swarm mission is for. In 2013, the European Space Agency launched 3 identical satellites into orbit around the Earth, and arranged them to fly in formation, some in a pair at one altitude and one higher up. Each carries an extremely precise magnetometer, an instrument that reads the strength and direction of the magnetic field wherever the satellite happens to be. Because the satellites are constantly circling the planet as the planet turns beneath them, they eventually cover the entire globe, ocean and land alike, over and over again. For more than a decade now, Swarm has been building something no previous generation could even dream of. A continuous moving map of the shield around our world, updated year after year, precise enough to catch changes that unfold across a single season. The raw readings from those satellites do not become knowledge on their own. Scientists feed them, along with data from the surviving ground observatories, into mathematical models of the field. One of the most important is called Chaos, built by researchers who have spent years refining it, and it is exactly what it sounds like it should not be. It is an attempt to bring order to the restless, shifting behaviour of the geodynamo by turning a flood of measurements into a clear picture of where the field is strong, where it is weak, and how fast each spot is changing. When you hear a specific number in this video, that the anomaly grew by a certain amount, that the field dropped by a certain percentage, that the weak spot is drifting a certain direction, that number almost always comes out of this marriage of satellites in orbit and models on the ground. And then there is the part that turns numbers into something you can actually feel. The Scientific Visualization Studio at NASA took the data on the South Atlantic anomaly and built a moving picture of it, tracing the weak spot from 2015 through 2025. When you watch that visualization, you're not looking at an artist's guess. You're looking at a measured, animated record of a hole in the Earth's magnetic field growing and shifting across a single decade. It creeps westward, it sinks further, and near the end, on the eastern side toward Africa, you can see the trouble starting, the first sign that the single soft spot is beginning to grow a second heart. That westward creep is not vague either. The whole anomaly drifts slowly toward the west at a measurable pace, a fraction of a degree of longitude every year, which adds up to it sliding a real distance across the map within a single human lifetime. And the split into 2 centres is not one lonely scientist's hunch. It shows up when independent teams feed the satellite and ground data into their separate models, the newer minimum toward Africa growing more intense while the older one over South America holds its ground. When several different analyses, built by different people using different methods, all resolve the same second low forming in the same place. That is the moment a strange result stops being noise and becomes a fact that somebody now has to explain. This is the point where I have to give you the numbers straight, because they are the spine of everything that follows, and because the story only earns its drama if the data is real. So here they are, as clearly as I can lay them out. The overall strength of Earth's main dipole field, the simple bar magnet part of the shield, has fallen by roughly 9% since Gauss measured it in the 1830s. That decline is not happening at the same rate everywhere. Over the South Atlantic, it is happening much faster than the global average. Since about 2014, the anomaly has expanded across an area close to half the size of continental Europe, something on the order of 2 million square miles of newly weakened sky. In one recent single year of measurement, the region grew by around 8%, and since roughly 2020, the fastest weakening of all has not been over South America, where the anomaly was first centered, but over a newer patch to the southwest of Africa. That shift, from one center to a second one pulling away toward Africa, is exactly what it looks like when a single anomaly starts to divide. I said at the top that the weak spot is splitting in two, and I want to be precise about what that means, because it is the most important new fact in this entire field of study. For as long as we have tracked it, the South Atlantic anomaly has had one minimum, one place where the field bottoms out. As of the most recent analysis, the models now resolve two separate cells of lowest field strength, two low points where there used to be one. For the satellite operators whose spacecraft have to survive passing through, this is not an abstraction. It means that where they once planned their radiation risk around a single danger zone, they may soon be planning around two. The hole in the shield is not just getting bigger, it is reorganizing itself into a shape we have never observed before. Now, a careful person hears all of that and asks the obvious grounding question. A field that has run for billions of years drops 9% in 200 years and grows a second weak spot, and we are supposed to be alarmed. 200 years is a heartbeat to a planet. Maybe this is just what the shield does. Maybe it wobbles, and we have simply never had good enough eyes to catch the wobble before. That is a completely fair objection, and holding on to it is going to make you smarter, not less informed as we go. But to know whether this is an ordinary wobble or the start of something rare, you cannot stay up here at the surface reading the numbers off a screen. You have to go down through the crust, down through the mantle, all the way to the churning metal engine where the field is actually born. Because the reason the shield is thinning over the South Atlantic and not somewhere else has almost nothing to do with the ocean above it, and almost everything to do with something enormous and strange sitting at the very bottom of the world. Part 3, 2,900 kilometers down. To understand why the shield is failing in one specific place, you have to stop thinking of the magnetic field as a thing that lives in the sky and start thinking of it as a thing that is manufactured continuously in a factory at the center of the Earth. And like any factory, it has a floor plan, it has machinery, and it has places where the machinery runs smoothly and places where it grinds. Start at the surface and go down. The crust, the part we live on, is a skin, thinner in proportion to the planet than the skin on an apple. Below it is the mantle, almost 3,000 kilometers of hot rock, so hot that over long enough spans of time it flows like extremely stiff tar, but rock all the same. And below that, starting at a boundary nearly 2,900 kilometers down, everything changes. You reach the outer core, and the outer core is not rock at all. It is liquid metal, iron and nickel, at temperatures somewhere in the neighborhood of the surface of the Sun. It wraps around a solid inner core, a ball of iron roughly the size of the Moon, which is under so much pressure that it stays solid despite being just as hot. The whole arrangement is one of the most extreme places in the known solar system, and it is sitting directly beneath your chair. That liquid metal outer core is where the magnetic field is born, and the process that makes it is worth slowing down for, because once you understand it, everything else in this story clicks into place. Heat is constantly trying to escape from the inner core outward, the way heat rises off a radiator. Hot liquid metal near the bottom of the outer core becomes slightly less dense and floats upward. Cooler metal sinks. That endless rising and sinking is called convection, and it is the same thing you see in a pot of water just before it boils, only here the pot is the size of Mars and the water is molten iron. Now add the fact that the entire Earth is spinning once a day. That spin grabs the rising and sinking columns of metal and twists them, through an effect named after the physicist Gaspar Gustave de Coriolis, into long corkscrewing spirals, all of them roughly lined up with the planet's axis. Here is the crucial link, the one piece of physics you need, and then you are done. Moving metal carries an electric charge along with it, and any time you move electric charge, you generate a magnetic field. The spiraling currents of liquid iron in the outer core are, in effect, a tangle of enormous electromagnets. And those electromagnets generate a field that, in turn, pushes on the moving metal in a way that keeps the currents organized and keeps them flowing. The field sustains the motion sustains the field. It is a loop that powers itself, drawing on the heat leaking out of the core to keep going, and it has been running for well over 3 billion years. This self-feeding engine is the geodynamo. When people say the Earth's core is what keeps us alive, this is the specific thing they mean. There is a beautiful wrinkle in what actually powers this engine, and it was first proposed more than a century ago in 1919 by a physicist named Joseph Larmor, who suggested that a rotating body of conducting fluid could generate its own magnetic field. The leftover heat from the planet's violent birth is part of the fuel, but it is not the whole story. Down at the boundary between the liquid outer core and the solid inner core, the Earth is slowly freezing from the inside out. The solid inner core is growing, a tiny amount at a time, something on the order of a millimetre of added radius each year, as the planet gradually cools across geological time. Every time a bit of iron freezes onto the inner core, it releases heat, and it also spits out lighter elements that had been dissolved in the metal, and those light elements go floating up through the outer core like bubbles rising through a glass of soda. That rising of light material stirs the outer core even more powerfully than heat alone, and it is now thought to be one of the main forces keeping the whole dynamo turning. Sit with how strange that is. The shield in your sky is powered, in part, by the slow freezing of a ball of iron at the centre of the Earth. And the field it produces is not vague. It ranges from roughly 25,000 nanotesla in its weakest regions to around 65,000 near the poles. Hold that number, because over the South Atlantic anomaly it sags to something closer to 22,000 nanotesla, and suddenly the weak spot is not an adjective. It is a measurement. Now, if the outer core were a perfectly smooth, perfectly even ball of spinning metal, the field it produced would be almost boringly simple. It would look like the field of a child's bar magnet, one clean loop running from a south pole to a north pole, tidy and symmetrical. Physicists call that idealized shape the dipole, and to a first approximation, that is what the Earth has. It is why a compass works. It is why we can even talk about a magnetic north and a magnetic south. Roughly 90% of the field at the surface is this clean, simple bar magnet part, but the outer core is not smooth and even, and that missing 10% is where this entire story lives. The real field is the tidy dipole plus a whole collection of lumps, bulges and irregularities layered on top, the fingerprints of a churning liquid that never flows quite the same way twice. Scientists call everything that is not the clean bar magnet the non-dipole field. It is the part that drifts, the part that grows and shrinks, the part that makes the difference between a shield that is even all the way around and a shield with a soft spot over the South Atlantic. If the dipole is the melody, the non-dipole field is every bit of static and distortion riding along with it, and it turns out that static is not random noise. Some of it is organized into features large enough and stubborn enough to carve a permanent-looking dent in the armor of the entire planet. To see how a churning core can leave a fixed weakness at the surface, we have to look at the boundary where the liquid metal meets the rock above it, the exact ceiling of that molten ocean, nearly 2,900 kilometers down. Because it is there, at the top of the core, that the field does something genuinely strange. In one region, and one region especially, the field lines are not pointing the way they are supposed to, they are pointing backward, and those backward patches are the reason a satellite over the South Atlantic has to close its eyes. Part 4. The patches that point the wrong way. Picture the magnetic field leaving the core the way light leaves a lamp, streaming outward, generally flowing out of the southern half of the planet and back into the northern half, the pattern a bar magnet would give you. Across most of the core's surface, that is exactly what happens. The field marches out in an orderly way, and by the time it reaches you at the surface, it is strong and well behaved. But at the top of the core beneath the South Atlantic, there are places where the flow has turned itself inside out. Instead of pointing outward the way the surrounding field does, the field in these patches points back inward, down into the core. Scientists call them reversed flux patches, and they are the villains of this story, or at least the mechanism behind the villainy. Think about what a backward patch does to the total field you measure up at the surface. Everywhere else, the field is adding up, all pointing the same general direction, reinforcing itself. But over a reversed patch, part of the field is now pointing the opposite way, and opposite pointing fields cancel. They subtract. So directly above one of these patches, the strength you measure is not the full strength of the shield. It is the full strength minus the part that is now facing the wrong way. Stack up enough reversed flux over one region, and the field there does not just weaken a little, it caves in. That caved-in region, measured from orbit, is the South Atlantic anomaly. The hole in the shield is, at its root, a place where the core's own field has turned against itself. Here is the arithmetic that makes it concrete. Out over a healthy stretch of the field, up near the poles, the strength runs to something like 65,000 nanotesla. Over the anomaly, once you subtract away everything the reversed patches are cancelling out, what is left can sink to around 22,000, roughly a third of the strong field value. The reversed patches do not have to flip the entire field to hurt you. They only have to cancel enough of it, over enough of an area, to open a soft spot the radiation can pour through, and these patches are not painted onto the core like markings on a map. They form when bundles of magnetic field lines get shoved up and expelled through the top of the core pointing the wrong way, dragged into position by the churning metal underneath. When that churning shifts, the patches grow, shrink, drift, or spawn new ones, and every one of those moves shows up weeks or years later as a change in the shape of the hole hanging over the South Atlantic. This is the answer to the question I planted a few minutes ago, the fair objection about whether 200 years of weakening really means anything. Because once you know the anomaly is caused by reversed flux patches at the top of the core, the behaviour we are watching from orbit stops being mysterious and starts being readable. When those patches grow, the anomaly grows. When they drift, the anomaly drifts. When a new patch begins to bloom off to one side, the anomaly starts to develop a second centre, which is exactly the splitting in two we can now see happening toward the African side. Everything Swarm is showing us at the surface is a shadow cast upward by what the field is doing at the ceiling of the molten core. We are not watching the weather, we are watching the shape of something far below projected onto the sky, and that reframes the whole question of how worried to be. A shield that is thinning because of a passing fluctuation might fill back in next decade. A shield that is thinning because reversed flux is expanding and multiplying at the top of the core is telling us something about the state of the engine itself. The reason nobody can yet say which one we are looking at is that these patches sit at a boundary we can never visit, under conditions we can barely reproduce, moving to a rhythm we have only just begun to record. We can see the shadow clearly. We are still learning to read the thing casting it. There is one more layer to this, and it is the layer that takes the story from strange to genuinely eerie, because it turns out the reversed patches are not scattered at random around the core. They keep showing up in the same part of the world, generation after generation of measurements, and further back, the magnetic memory locked into ancient rocks and pottery. All point to the same conclusion. The South Atlantic has been a troubled region of the field not just for decades, not just for centuries, but for far longer than that. Something keeps steering the weakness back to this same corner of the planet again and again, and when scientists went looking for what could possibly reach up from below and organise the behaviour of a spinning ocean of metal, they found it sitting at the very bottom of the mantle, a structure so large and so old that it may have been shaping the Earth's magnetic field since before there were human beings to carry a compass. To meet it, we have to go down one final time, past the core mantle boundary, to a buried continent that no one will ever see. Part 5. The Continent. At the bottom of the world. At the base of the mantle, where the hot rock finally meets the liquid metal of the outer core, the Earth hides two enormous secrets. They sit on opposite sides of the planet, one beneath Africa and one beneath the Pacific, and until a few decades ago we had no idea they existed. We cannot dig to them. We cannot photograph them. We found them the only way anyone ever could, by listening to earthquakes. When a large earthquake shakes the planet, it sends seismic waves rippling all the way through the interior, and those waves change speed depending on what they travel through. By collecting the arrival times of earthquake waves at stations all over the world, scientists can build something like a medical scan of the inside of the Earth, a way of mapping regions that are hotter or cooler, denser or lighter, without ever touching them. And when they turned that scan on the bottom of the mantle, they found two colossal blobs where the seismic waves slowed down dramatically. Two structures, each larger than a continent, rising hundreds of kilometers up off the core like mountains hanging from the ceiling of the mantle. The scientific name is a mouthful. Large, low-shear velocity provinces. Most people who study them just call them the blobs. The one that matters for our story is the one beneath Africa. These two blobs even have nicknames among the researchers who study them. The one under Africa is sometimes called Tuso, and the one under the Pacific is called Jason, named after pioneering geophysicists. Each rises perhaps hundreds of kilometers up off the core, with some estimates putting the tallest parts near 1,000 kilometers of relief, and each spans a region of the planet's interior thousands of kilometers across. They are, in the most literal sense, mountains the size of continents hanging from the underside of the mantle. And there is a genuinely wild idea about where at least some of this material might have come from. One recent line of research suggests the blobs could be buried remnants of Theia, the Mars-sized world that, according to the leading theory, slammed into the young Earth and threw off the debris that became our moon. If that turns out to be right, then the structure steering our magnetic weak spot today may be a piece of another planet, entombed at the bottom of the mantle for 4.5 billion years. Whatever they truly are, at their ragged edges sit even stranger patches where seismic waves slow almost to a crawl, hinting at pockets of partly molten rock pressed right against the core. This is the neighbourhood that quietly decides where our shield runs thin. Nobody's completely certain what these things are made of, and that uncertainty is part of what makes them so unsettling. The leading idea is that they are piles of material that is both hotter and denser than the mantle around them, possibly ancient, possibly the graveyards of oceanic plates that sank over billions of years, possibly even older material left over from the Earth's violent formation. Whatever they are different from their surroundings, and they have most likely been sitting in roughly the same place for an immense span of time, maybe hundreds of millions of years, maybe longer. Now remember where this one sits. The African blob is parked at the bottom of the mantle, directly below the region where our magnetic shield is weakest. That is not a coincidence anyone believes anymore. Here is how a mass of rock at the bottom of the mantle can reach up and bruise the magnetic field being made in the core below it. The geodynamo runs on heat escaping from the core. How smoothly and evenly that heat gets to leave depends on what is sitting on top of the core waiting to carry the heat away. Where the mantle above the core is normal, heat flows out in the ordinary way, and the field-making currents underneath behave themselves. But directly under Africa, the core is capped by this dense, hot, abnormal pile. It changes how heat leaves the core in that region, and by changing the heat flow, it changes the pattern of convection in the liquid metal directly beneath it, nudging the currents into arrangements that favour exactly the thing we do not want: the growth and expulsion of those reversed flux patches. The blob at the bottom of the mantle is, in effect, reaching down into the engine and putting a thumb on it. Scientists call this idea top-down control, the mantle steering the dynamo from above, and it is the leading explanation for why the South Atlantic keeps being the soft spot in the shield across enormous stretches of time. The researcher whose name comes up most often here is John Tarduno, who with his colleagues published work arguing that the South Atlantic anomaly is not some recent accident of the last few centuries. By reading the faint magnetic memory frozen into ancient materials, they found evidence that this same region has been a recurring site of a weak, disturbed field going back not just thousands, but potentially millions of years. If that is right, then the anomaly over our heads today is the latest chapter of a very old book, one written in the strange geography far beneath the surface. The blob has been there a long time. The weak spot keeps coming back to sit above it. Tarduno and his colleagues built part of their case from an unlikely archive. In southern Africa, farming communities more than 1,000 years ago would, during severe droughts, ritually burn their grain bins and clay huts, and the intense heat locked the direction and strength of the magnetic field into the baked clay at that moment, the same way a cooling lava flow does. By reading those burned floors, researchers found that the field over the region had passed through episodes of sharp weakness before, long before any satellite or observatory existed, in the same corner of the world that is weak today. It was direct physical evidence that the South Atlantic tendency toward a soft field is not a modern accident. It is a habit of the Earth's interior, one this region has returned to again and again across time, whenever the buried continent below nudges the engine the wrong way, and this is the fork in the road for the entire story, the reason I keep circling back to the same unanswered question. If the anomaly is an ancient recurring feature ruled by a structure that has sat under Africa for ages, then maybe what we are watching is genuinely just the planet breathing. A slow rhythm we finally have the instruments to notice. That is the calm reading, and it has real evidence behind it. But an ancient tendency toward weakness and a full-blown collapse are not the same thing, and knowing that the South Atlantic has always been the vulnerable spot does not tell you how far the current weakening will go. The blob explains where, it does not explain how much or how fast, or whether this particular episode stops at a dent or keeps going. To get any handle on that, we need something the surface measurements and the seismic scans cannot give us. We need a preview. We need to find a time when the field actually did collapse and see what happened to the world when it did. As it turns out, we have exactly one such record, written into the growth rings of a tree that died 42,000 years ago. Part 6. The only preview we have. Everything I have told you so far has been about a shield that is weakening. Now, I have to tell you about the one time in the recent history of the planet when the shield very nearly failed altogether, because it is the closest thing we have to a look at the stakes, and the strangest part is how we know about it, which is that a single ancient tree pulled dead and preserved out of a swamp in New Zealand ended up carrying a timestamp for a global catastrophe. First, the concept you need. The full flip of the magnetic field, where magnetic north and magnetic south trade places and stay traded, is called a reversal, and I will come back to those in detail later. But there is a smaller, more common cousin of the reversal, and that is what matters here. Sometimes the field starts to flip, weakens dramatically, wanders, and then, instead of completing the switch, it recovers and settles back the way it was. A failed flip, essentially. Scientists call these events excursions. During an excursion, the field can drop to a tiny fraction of its normal strength before bouncing back. And the most famous excursion in the recent geological record has a name. It is called the Lachamp event, and it happened between roughly 42,000 and 41,000 years ago. The event is named for a place, as these things often are. In the 1960s, researchers studying old volcanic rocks at a site called Lachamp in central France found lava that had cooled with its magnetism pointing the wrong way, the frozen record of a field that had briefly turned itself around. That single strange outcrop gave the whole event its name, and later work traced the same signature in sediments and ice and rock all over the planet, confirming that this was not a local fluke but a worldwide episode. What one hillside in France first hinted at, the rest of the globe eventually confirmed. During the Lachamp excursion, the Earth's magnetic field did not just weaken the way ours is weakening now, it very nearly went out. At the extreme of the event, the field is estimated to have fallen to somewhere between 0 and 6% of its normal strength. Sit with that range for a moment, because it is staggering. Our field today, after 9% of decline that has scientists paying close attention, is still at over 90% of its recent strength. During the depth of Lachamp, the shield around the entire planet may have dropped to almost nothing, for a geologically brief window, and then clawed its way back. For a few centuries, our ancestors lived under a sky whose protection had all but switched off. The problem with an event that old is anchoring it precisely in time. Ordinary carbon dating gives you a range, not a stopwatch, and to understand what a collapsing field did to the climate and to living things, you need to line up events with real precision. This is where the tree comes in. In New Zealand, giant kauri trees can live for thousands of years, and when they die and fall into a bog, the airless mud can preserve their wood for tens of thousands more. One such kauri, dug up for study, had lived straight through the window of the Lachamp event, laying down a growth ring every year the entire time. Locked in those rings was a record of the atmosphere year by year, including a spike in a form of carbon that is produced when radiation from space crashes into the upper atmosphere. When the magnetic shield weakens, more of that radiation gets through, and more of that special carbon gets made. The size of that carbon spike is a big part of what makes the kauri so valuable. Across the window of the event, the amount of radiocarbon being produced in the atmosphere climbed sharply, and because the tree laid down a fresh ring every single year for the entire period, roughly 1,700 years of unbroken record in that one log, researchers could trace the rise and fall of incoming cosmic radiation almost year by year. Pause on how improbable that is. A single tree started growing before the event, lived through the whole collapse and recovery, died, and then lay preserved in an airless bog for more than 40,000 years, waiting for someone to dig it out and read the ancient sky straight out of its growth rings. Without a natural clock that precise, the entire event would be a blur on the timeline instead of a dated year-by-year sequence you can actually study. The Cowrie had recorded the collapse of the shield in its own body, ring by ring, like a tree-shaped seismograph of the sky. Two researchers in particular, Alan Cooper and Chris Turney, used that Cowrie record as the anchor for an ambitious reconstruction, published in the journal Science in 2021. They took the precise timing the tree gave them and layered onto it everything they could gather about the climate, the chemistry of the atmosphere, and the living world during the same window. They gave the most dramatic phase of the event its own name, the Adams event, and they painted a picture of what it might have been like to live through the near death of the magnetic field. It is a genuinely cinematic picture, and, as we will see, it is also a contested one, because the line between what the tree proves and what the researchers proposed is exactly the kind of line this channel exists to walk carefully. First, though, let me show you the world they described, because whether or not every claim holds up, the physics underneath it is real, and it is the clearest answer we have to the question of what a dying shield actually does to the sky. Part 7. The Sky Our Ancestors Saw. Imagine you're alive 42,000 years ago. You're a modern human, anatomically identical to us, living through the last ice age, and you have never needed to think about the sky as anything other than the thing weather comes from. Then, over the span of a few generations, the sky begins to change and no one has any way to understand why. Start with the part we are most confident about, because it follows directly from the physics we have already built. When the magnetic field collapses toward almost nothing, the barrier that funnels charged particles toward the poles stops working. Normally, the solar wind and the particles it carries get steered up to the far north and far south, which is why the auroras, the northern and southern lights, are things you have to travel toward the poles to see. Strip the field down to a few % of its strength, and that funnel falls apart. The particles can pour in almost anywhere. The auroras would have unhooked from the poles and wandered, appearing in skies that had never seen them, shimmering curtains of light over the tropics, over the equator, over people who had no framework at all for what they were looking at. A recent study reconstructing the position of the auroras during this period found exactly this kind of wandering, the whole light show drifting far from where it belongs. For our ancestors, the most reliable thing in the world, the sky itself, would have started doing things it had never done. Now the more serious layer, the one that is not just beautiful but dangerous. The magnetic field is only the first of the shields between us and space. It works together with the ozone layer high in the atmosphere, which absorbs most of the sun's ultraviolet radiation before it reaches the ground. When the magnetic field weakens and lets more energetic particles and cosmic radiation flood into the upper atmosphere, the radiation can chemically attack the ozone layer, thinning it. And a thinner ozone layer means more ultraviolet light reaching the surface, the same ultraviolet that burns skin and damages the living cells of anything exposed to too much of it. Cooper and Turney argued that during the Adams event, the combination of a collapsed magnetic field and a damaged ozone layer would have driven a real spike in ultraviolet radiation at the surface across the middle latitudes of the planet, the shield above and the shield within failing at the same time. From there, their reconstruction reached outward into the living world, and this is where it became genuinely provocative. They proposed that this pulse of radiation, and the climate disruption that came with it, lined up with a whole cascade of changes in the archaeological and fossil record. They pointed to the extinction of giant animals in Australia, the megafauna that vanished around this broad window. They pointed to the disappearance of the Neanderthals in Europe, who faded out of the record in roughly the same era. And most strikingly, they pointed to the explosion of figurative cave art that appears across Europe and Southeast Asia around this time, suggesting that people driven into caves for shelter from a hostile sky, perhaps even smearing themselves with red ochre as a kind of primitive sunscreen, left behind the first great flowering of human painting on those cave walls. In their telling, the near death of the magnetic field was not a footnote, it was a hinge in the human story, a moment when the failing shield reshaped life, death, and art all at once. It is a spectacular picture, and if it is true, it is the single best answer anyone could give to the question of why a weakening shield should keep you up at night. A collapsing field does not just scramble satellites, it rewrites the sky, thins the ozone, floods the surface with ultraviolet, and reaches into the fate of entire species. That is the version of this story that goes viral, and you have probably seen a headline shaped like it. But you come to this channel because I do not stop at the version that goes viral. The honest scientist in the room has to ask a harder question. How much of that dramatic cascade did the tree actually prove, and how much of it did two researchers propose, connect, and lay on top of the timeline the tree gave them? Because the answer to that question is where the real intellectual honesty of this story lives, and it matters enormously for how you should feel about the anomaly growing over our own heads right now. Part 8. What the tree can and can't prove. Here is the rule I try never to break on this channel. When a story is this good, that is exactly when you slow down and check which parts are measured and which parts are argued. The Lachamp event gives us a clean case study, because the evidence sits at very different levels of certainty, and telling them apart is the whole game. Start with what is solid, because a lot of it is. That the Lachamp excursion happened is not in doubt. It is recorded in rocks and sediments all over the world, in the magnetic minerals that lock in the direction and strength of the field at the moment they cool or settle. That the field dropped to a small fraction of its strength during the event is well supported by those same records. That a weakened field lets more cosmic radiation into the upper atmosphere, and that this produces more of the special carbon found spiking in the Carey tree, is straightforward physics and chemistry, and the spike in the tree is real data you can measure ring by ring. That auroras would wander during such an event follows directly from the physics, and has independent support. All of that is the strong core, and none of it depends on anyone's interpretation. The shield really did nearly fail, and the sky really did change. Now the part that has drawn serious pushback. The leap from the field collapsed and radiation rose to the field collapse, caused the megafauna extinctions, ended the Neanderthals, and drove people into caves to invent art is a very different kind of claim. It is a chain of cause and effect stretched across events that are each independently complicated, each with their own competing explanations, and each dated with real uncertainty. And when specialists in those fields looked at the chain, many of them were not convinced. Archaeologists pointed out that the Neanderthals did not vanish everywhere at once, and that their decline was a drawn-out, patchy process that does not line up neatly with a single sudden event. The dates make the point sharper. The best evidence suggests Neanderthals were already fading across Europe over thousands of years, with many populations gone before the magnetic event even reached its depth, which makes it hard for that event to be the trigger for a disappearance that was largely already underway. Australia's giant animals tell a similarly untidy story, with different species vanishing at different times across a long span, and with the arrival of humans and their hunting standing as a well-supported pressure long before anyone reached for the magnetic field as an explanation. None of this proves the radiation pulse did nothing at all. It means the clean single-cause version, the field faltered and the world emptied out, does not survive contact with the actual dates. The real history was slower, messier, and pushed by several forces at once, which is very nearly always how these enormous changes actually unfold. Scientists who study the great extinctions noted that Australia's giant animals disappeared over a range of dates, with human hunting and longer-term climate change as long-standing, well-supported drivers. Researchers who study cave art pointed out that the tradition did not simply switch on at one instant. Today, most archaeologists and specialists who work on this period treat the strong version of the Cooper and Turney claims, the idea that a magnetic event was the trigger for those extinctions and cultural changes, as not established. Not disproven in every particular, but not demonstrated and not the consensus. I want to be careful and fair here because dismissing the whole thing would be as lazy as swallowing it whole. The researchers were not making things up. They anchored a real event with a genuinely clever piece of dating, and they proposed a bold, testable idea about its consequences. That is how science is supposed to work. The bold idea then met the scrutiny of specialists, and the parts that could not be supported got pushed back. What survives that process is important and sobering enough on its own. A weakened magnetic field, working together with a damaged ozone layer, really can raise the level of harmful radiation reaching the surface of the planet. That is not fringe. That is the mechanism, and it is real. What remains unproven is the size of the biological consequences the last time it happened, not the existence of a mechanism that could cause them. So carry both halves of this forward, because we're about to turn back to our own time, and both halves matter. The measured half tells you that a collapsing shield genuinely changes the sky and can flood the surface with ultraviolet. The contested half is a warning about the other direction, the temptation to take a real physical danger and inflate it into a story of civilizational doom that the evidence does not support. Hold on to both, because the anomaly over the South Atlantic is going to tempt you in exactly those two directions at once. And the truth, as usual, is going to sit in the uncomfortable space between them. To find it, we have to come back up out of ancient history and ask a very present-day question. What is the thinning shield already doing to us right now, with the technology our entire civilization is built on? Part 9. The Machines in the Firing Line. The comforting thing about the Lachamp event is that it was 42,000 years ago. The uncomfortable thing about the South Atlantic anomaly is that it is charging our credit card today, because while nobody is claiming the current weakening is anywhere near a full collapse, the shield does not have to fail completely to start costing us. It only has to thin over the wrong place, and the wrong place turns out to be directly in the path of the machines our modern lives quietly depend on. Here is the physics of the damage, kept simple. Space around the Earth is not empty. It is threaded with fast-moving charged particles, some from the Sun, some from far outside the solar system, and many of them trapped in two enormous rings around the planet called the Van Allen belts. The magnetic field is what holds those belts up and away from us. But over the South Atlantic anomaly, where the field is weak, the inner belt sags downward until its bottom edge is only about 200 kilometers above the surface. That is right in the neighborhood where satellites in low orbit fly and where the space station circles. So a satellite crossing the anomaly is not passing through empty sky. It is wading through the drooping bottom of a radiation belt. When one of those high-energy particles slams into the electronics of a spacecraft, it can dump its charge into a tiny transistor or memory cell and flip a bit, turning a 0 into a 1 or a 1 into a 0. Engineers call this a single-event upset. Most of the time it is harmless, a single wrong number in a sea of right ones, quietly corrected. But sometimes that flipped bit is in exactly the wrong place, and the satellite does something it should not. Its computer glitches, its data comes back corrupted, a command misfires. In the worst cases, the particle strike can latch up a circuit and cause real, permanent damage. Studies of satellite malfunctions have found that a strikingly large share of them happen in one specific region of the globe, and you can already guess which one. They cluster over the South Atlantic anomaly. Operators around the world have learned to treat this stretch of sky as a hazard to be managed, a place where you brace for errors. We have only known those radiation belts exist since 1958, when the very first American satellite, Explorer 1, carried an instrument built by the physicist James Van Allen and discovered the enormous rings of trapped particles that now carry his name. Think about the pace of that. In the span of a single human lifetime, we went from not knowing the belts were there at all to launching tens of thousands of satellites straight toward the region where those belts dip lowest. Consider the scale of what now rides in that zone. A single company's internet constellation already numbers in the thousands of spacecraft in low orbit, and the total number of active satellites circling the planet has climbed into the tens of thousands, with more going up nearly every week. A great many of them fly at exactly the altitudes where the sagging inner belt does its damage. Individual satellites have logged memory errors, unexpected reboots, and instrument glitches concentrated over this one region of the globe, and mission operators file the anomaly into their planning the way a pilot files a known patch of turbulence on a route. The difference is that this patch of turbulence is slowly growing, and unlike weather, it is not going to pass by tomorrow. Now, connect that back to what the field is doing. The anomaly is growing by an area close to half of Europe since 2014, it is growing more intense, and it is splitting into two centres, which means the hazard zone is not only expanding but multiplying, turning one region operators have to plan around into potentially two. Every year, we launch more satellites into low orbit, thousands upon thousands of them now, for internet, for imaging, for navigation, for science. We are packing more and more of our critical infrastructure into exactly the altitude band where a growing hole in the shield does its damage. The weak spot and our dependence on the machines it threatens are both increasing at the same time. That is not a coincidence that will resolve itself quietly. That is two curves heading toward each other, and this is the point where the story stops being about a number on a scientist's screen and starts being about you. The satellite that reroutes when its navigation glitches over the anomaly is the same kind of satellite your phone talks to. The imaging spacecraft that loses a few minutes of data is part of the same fleet that watches storms and crops and coastlines. We have built a civilization that leans on a thin shell of machines just above the atmosphere, and the shield that protects that shell is developing a hole underneath the busiest part of it. The most valuable of those machines have already been forced to take defensive measures, and one of them is so precious that when it reaches the anomaly it simply refuses to work. To understand how seriously the people who run these missions take this, look at what they are willing to give up every single day to protect their hardware. Part 10. Why Hubble closes its eyes. The Hubble Space Telescope is one of the most productive scientific instruments ever built. For decades it has been sending back the images that reshaped how we picture the universe, the swirling galaxies and glowing pillars of gas you have seen 100 times without necessarily knowing where they came from. Time on Hubble is among the most sought-after and expensive resources in all of science, and for a chunk of every single day, that priceless telescope stops collecting some of its data on purpose because it is passing over the hole in the shield. Hubble orbits low enough that it crosses the South Atlantic anomaly on many of its trips around the planet. When it does, the radiation environment gets bad enough that its most sensitive detectors are at risk, both of damage and of having their observations ruined by particle strikes streaking across the image. So the operators built the anomaly into the telescope's routine. Certain instruments get their high voltage reduced or switched off during the crossings. Observations get scheduled around the passages. In practice, a meaningful fraction of Hubble's orbit is a no-go zone for delicate science, carved out of the sky by a weakness in the Earth's own magnetic field. Think about the strangeness of that. We built a machine to see to the edge of the observable universe, and there is one patch of sky above our own ocean where it has to look away. The space station tells the same story in an even more human way, because the space station has people on it. The International Space Station also passes through the anomaly, and up there the radiation is not just a threat to electronics, it is a dose to living bodies. Astronauts crossing the anomaly take on more radiation than they do elsewhere in the orbit. The station carries extra shielding to help manage it. Sensitive equipment gets extra protection, and when astronauts go outside for a spacewalk, stepping out of the metal hull with only their suits between them and space, mission planners deliberately schedule those excursions to avoid the times when the station is crossing the weak spot. The people who actually live above the atmosphere organize their most dangerous work around the geography of a hole in the shield. They have to. For them it is not a curiosity from a science channel, it is a daily fact of staying safe. Astronauts have even reported a stranger, more intimate sign of the anomaly. Some have described seeing flashes of light with their eyes closed while passing through high radiation regions, faint sparks caused by charged particles passing directly through the eye and the visual system. When a person can perceive the failing shield as flickers of light inside their own head, the abstraction is gone. This is radiation that a human being can, in a sense, feel. Astronauts have been reporting those flashes since the Apollo missions to the Moon. When crews first described seeing streaks and pinpricks of light with their eyes closed, eventually understood as cosmic ray particles passing directly through the eye and the nerves behind it. It was one of the earliest hints of how exposed the human body becomes once you climb above the thickest part of the shield. Over the anomaly, that exposure spikes in a place low enough that crewed stations pass through it on a routine basis, which is exactly why the radiation dose logged by people living in orbit is not spread evenly around their path. It piles up in the same patch of sky that forces Hubble to shut its eyes, the same patch that scrambles satellite memory, the same growing, splitting weak spot we have been chasing from the ground floor of this story. Everything keeps circling back to the one hole in the shield. And here is the through line, the reason all of this belongs in the same story as ancient trees and buried continents. Every one of these defensive measures exists because the field is weak in one place, and every one of them will have to be taken more seriously as that weak place grows and divides. We are not waiting for the shield to fail in some distant future. We are already rearranging how we operate in space around the part of it that has already thinned. That is the present tense of this story. But there is one more present tense danger, and it is the one that ties this whole subject back to the storms this channel watches most closely. Because a thin shield is not only a problem on a calm day. A thin shield is a very different kind of problem on the day the sun decides to throw everything it has straight at us. Part 11. When the sun and the weak spot meet. If you have spent any time here before, you know the sun is not a quiet neighbour. We have watched it tear open coronal holes and fling high-speed streams of plasma at the Earth. We have tracked the enormous sunspot regions that twist their magnetic fields into knots and then snap, launching billion-ton clouds of charged particles across the 93 million miles of space between us and them. We have talked about what happens when one of those clouds hits our magnetic field and sets off a geomagnetic storm, lighting up the auroras and pushing dangerous electrical currents into power grids. History has already shown us what the strong version of this looks like, even with the shield at full strength. In 1859, the largest geomagnetic storm in recorded history, now called the Carrington event, struck a world that had just started stringing telegraph wire across its continents. The storm drove currents so strong that telegraph systems failed. Operators reported sparks leaping from their equipment, some lines caught fire, and the auroras were seen almost down to the equator, so bright in places that people woke in the middle of the night thinking morning had come. Closer to our own time, in March of 1989, a solar storm pushed currents into the power grid of Quebec and collapsed the entire system in about 90 seconds, dropping roughly 6 million people into darkness for around 9 hours in the depths of a Canadian winter. And in 2022, a fairly ordinary storm was enough to warm and puff up the outermost edge of the atmosphere, just enough to drag dozens of freshly launched satellites back down to burn up before they ever reached a stable orbit. Now picture those same blows landing on a shield that has thinned, over the exact region where it is already weakest. That is the multiplication I keep pointing at, and it is not a hypothetical. It is the same physics that has already darkened whole cities, aimed at a softer target. Every one of those stories had a silent assumption baked into it, and it is time to say the assumption out loud. All of that coverage assumed the shield was doing its job at full strength. What happens when it is not? Here is the connection that ties this entire video to the storms we track. The magnetic field is the thing that catches a solar storm and steers most of its energy around the planet. The stronger the field, the better it deflects and absorbs the blow. A weaker field is a thinner catcher's mitt. When the shield is already reduced, a given solar storm can push farther into near-Earth space before the field stops it, which means the storm's effects can reach lower altitudes and lower latitudes than they otherwise would. Over a region like the South Atlantic anomaly, where the field is weakest and the radiation belts already hang low, a big storm has the least resistance to push against. The weak spot is the crack in the armour, and a solar storm is a blow aimed at armour. You do not need me to tell you what a blow does when it finds the crack. This matters on a human timescale, not a geological one, and that is what makes it urgent in a way the ancient history is not. We do not have to wait 42,000 years for the field to matter. The sun is active right now, in the current stretch of its 11-year cycle, and it will keep throwing storms at us for years to come. Each one of those storms arrives at a planet whose shield is a little thinner than it was for our grandparents, and thinnest of all over a growing patch of the southern sky. A storm that would have been shrugged off a century ago may not be shrugged off as easily today. Satellites already stressed by crossing the anomaly are the same satellites that have to ride out a solar storm. The two hazards do not add up. They multiply. I want to be careful not to overstate this, because the honest position is still that our field, for all its weakening, remains strong enough to hold off ordinary storms, and the sky is not about to fall. But careful is not the same as calm, and the trend is the thing to watch. A shield that keeps thinning over a patch that keeps growing, meeting a sun that keeps firing, is a set of curves that only points one direction. It is the reason a story about the slow drift of metal far below the ground is not an academic one. It reaches all the way up to the satellites over your head and the grid that feeds your home on the day the next great storm arrives. And remarkably, the South Atlantic is not even the only place the shield is visibly on the move. On the far side of the planet, the very compass point of north has torn loose from where it sat for centuries and started to run. Part 12. The Pole that Walked Away from Canada. Take out a compass, let the needle settle, and it will point north. Except it will not point to the true North Pole, the fixed point at the top of the world where the axis of the planet comes through. It points to the magnetic North Pole, which is a different place entirely, set not by the spin of the Earth but by the behaviour of that churning metal core we have been circling this whole time. And here is the fact almost nobody carries around in their head. The magnetic North Pole does not stay put. It moves. It has always moved. And over the last few decades it has started to move in a way that has forced the entire world to redraw the maps that ships, planes, and phones use to find their way. We have known where the magnetic pole was for a surprisingly long time. In 1831, a British explorer named James Clark Ross, during one of the great Arctic expeditions of that era, physically stood at the spot in the Canadian Arctic where his instruments told him the magnetic field pointed straight down into the ground. That is the definition of the magnetic pole, the place where the field is vertical, where a perfectly balanced needle would try to dive straight into the Earth. This gap between where a compass points and where true north actually lies even has a name, declination, and it has bedeviled navigators for centuries. A sailor could never simply trust the needle, because the difference between magnetic north and true north changes depending on where you stand on the globe and drifts over time as the field itself shifts. Get that correction wrong over a long ocean crossing and you could miss your destination by a wide margin, a mistake that in earlier centuries could cost a ship and everyone on it. It is the reason careful mariners have always needed up-to-date magnetic charts, and it is the reason a moving pole is not a piece of trivia but a working problem. When the pole runs, the declination at millions of points on the map quietly changes, and every chart that assumed the old value slowly becomes a small spreading lie. Ross planted the first real marker. For the next century and a half, the pole stayed in the same general neighbourhood, wandering slowly around the islands and frozen seas of the Canadian Arctic, drifting a few kilometres a year, a lazy, meandering walk that mapmakers could easily keep up with. If you had checked on it every decade across the 1800s and most of the 1900s, you would have found it more or less where you left it, shuffling around northern Canada. Then, near the end of the 20th century, the lazy walk turned into a run. The magnetic pole picked up speed, straightened its path, and set off across the top of the world, leaving the Canadian Arctic behind and striking out across the Arctic Ocean directly towards Siberia. This was not a subtle drift you needed sensitive instruments to argue about. The pole covered ground fast enough that within a human lifetime, it moved a distance you would measure in thousands of kilometres. It has now travelled more than 2,200 kilometres from the position where explorers first pinned it down. It crossed the international date line. It left the Canadian side of the Arctic entirely and headed for the Russian one, the point that every compass on Earth answers to picked up and marched most of the way across the polar sea. Curiously, the pole at the bottom of the world does not mirror the one at the top. You might reasonably expect the South Magnetic Pole to sit exactly opposite the North Magnetic Pole, but it does not, and it never has. The two poles wander independently, at different speeds, and in different directions, and a straight line drawn through the planet from one to the other would miss the centre of the Earth entirely. That mismatch is itself a fingerprint of everything we have been circling, the lumpy, non-dipole part of the field, the deviation from a clean bar magnet. If the Earth were a simple magnet, its poles would be tidy opposites. They are not, because the engine that makes them is a churning, uneven flow of metal, and the southern pole answers to a different stretch of that flow than the northern one does. Two poles, two separate walks, one restless core beneath them both, quietly reminding us that the field has never been as simple or as steady as the word north makes it sound. Stop and feel how strange that is, because familiarity hides it. North is supposed to be the one direction you can trust. It is the anchor of every map, the reference for every journey, the thing sailors staked their lives on for centuries. And that anchor has been sliding across the Arctic at a pace that turns navigation charts obsolete. The reason takes us right back to the core, because the pole is not an object that can be pushed around. It is a symptom, a surface marker for the state of the field, and when it bolts across the Arctic, it is telling us that something in the metal engine below has shifted its balance. The same restless core that is thinning the shield over the South Atlantic is, at the very same time, dragging the compass point of north toward Russia. Two symptoms, one cause, and the cause, it turns out, is a tug-of-war between two patches of raw magnetic force, buried on opposite sides of the Arctic. Part 13. The tug-of-war in the core. To understand why the pole ran, picture the top of the core not as a smooth surface but as a landscape, with a few especially intense features, concentrations of magnetic flux where the field bunches up and pours out with extra strength. Two of these matter for the North Magnetic Pole. One sits under Canada, one sits under Siberia, and the position of the pole at the surface is, in a real sense, decided by the balance of power between them, like a rope with a knot in the middle being pulled from two ends. For a century and a half, the Canadian patch had the stronger grip, and so the pole loitered over Canada, held in place by the tug from below. Then, over the last couple of decades, the balance broke. Careful analysis of the field showed that a river of molten iron in the outer core had shifted, and the flow of metal that fed the Canadian patch began to move away, stretching and weakening it, while the Siberian patch held firm and effectively won the contest. The moment the Canadian grip failed, the knot in the rope lurched toward the stronger side, and the pole took off toward Siberia. This is not a metaphor scientists reach for to sound dramatic. It is the mechanism, worked out from the data, and it is why the pole's dash lines up in time with measurable changes in the pattern of flux at the top of the core. The pole ran because far below, the plumbing that sustains the field rearranged itself. Then the story took another turn that nobody had predicted. Having sped up to a remarkable pace, somewhere around 55 to 60 kilometers per year at its fastest through the 1990s, the pole recently began to slow down. Not stop, but decelerate, easing back to something closer to 35 kilometers per year. And when researchers measured that slowdown, they realized they were looking at the largest single deceleration in the pole's speed ever recorded. First an unpredicted sprint, then an unpredicted braking. The engine sped the pole up, and then the engine reined it back in, and both moves caught the experts off guard. Along the way, the pole did something quietly symbolic. As it marched off the Canadian side of the Arctic and out across the top of the world, it passed close by the geographic North Pole and crossed the prime meridian, the zero line of longitude that runs down through Greenwich in England, and kept right on going toward the Siberian side. The compass point that defined north for the entire age of European exploration walked out of the Western Hemisphere and into the eastern one within living memory. Where it heads next and how quickly depends entirely on that hidden tug-of-war between the flux lobes far below, which is really just another way of admitting we will find out when the core decides to show us. That element of surprise is the part I want you to hold on to, because it is the honest heart of this entire subject. The people who study the geomagnetic field are among the sharpest scientists we have, working with satellites and models of extraordinary precision, and even they did not forecast the pole's sprint and did not forecast its sudden braking. The core does not send us a schedule. It does what it does, driven by the flow of liquid metal we cannot see and cannot fully model, and we find out afterward. That is exactly why the growing hole over the South Atlantic is so hard to call. The same system that surprised us with the pole is the system now thinning the shield and splitting the anomaly in two. When the experts tell you they cannot yet say whether the weakening is routine or the start of something rare, this is why. They have watched this core juke them twice in one lifetime already, but surprise or not, a pole that will not sit still creates a very concrete, very modern problem, one that reaches into the navigation system in your pocket. Because when north moves, every map that assumed it would stay put is suddenly, quietly, wrong. Part 14. Redrawing the world's maps. There is a document you have never heard of that quietly sits underneath a huge amount of modern life. It is called the World Magnetic Model, and it is the official agreed-upon mathematical description of the Earth's magnetic field, the master map of where the field points and how strong it is at every spot on the globe. It is produced jointly by the National Centres for Environmental Information at the American agency NOAA and by the British Geological Survey, and it is the reference that navigation systems around the world quietly rely on to reconcile the direction a compass gives with the direction of true north. Every time a system needs to know the gap between magnetic north and geographic north at your exact location, it reaches, directly or indirectly, for this model. The catch is that the model is only as good as its assumptions about where the field is going, and the field, as we have just seen, does not cooperate. The world magnetic model is normally updated on a 5-year schedule, the idea being that the field drifts predictably enough that a fresh version every 5 years keeps everyone accurate. But the magnetic pole's dash towards Siberia got fast enough and unpredictable enough that the normal schedule could not keep up. The error between the model and the real field grew so quickly that, ahead of the regular update, the agencies took the rare step of issuing an emergency out-of-cycle correction to the world magnetic model, so that navigation systems would not drift out of tolerance before the scheduled version arrived. The timing of that emergency fix is almost darkly comic. It was due at the very start of 2019, and its public release was actually held up for several weeks by an American government shutdown. So for a short stretch, the corrected map of the entire planet's magnetic field was finished and ready, but stuck behind a bureaucratic door. When it finally came out, it quietly updated the navigation backbone for everyone downstream, most of whom never knew a thing had happened, and the drift reaches right down to the ground in ways you can literally see painted onto the world. Airport runways are numbered by their magnetic heading, rounded to the nearest 10 degrees, so a runway pointing near 90 degrees is called runway 9. But as magnetic north keeps sliding, those headings slowly fall out of date, and airports have had to repaint their runway numbers and reissue their charts to keep the signs honest. One of Florida's largest airports had to do exactly that more than a decade ago, temporarily closing a runway to renumber it because the field had drifted far enough to demand it. When someone asks why anyone should care about a wandering pole, that is the answer. We have quietly baked the assumption of a fixed north into everything from a submarine's compass to the number painted on a runway to the little arrow on your phone screen, and the core does not care in the slightest what we assumed. Think about that for a moment. The pole moved fast enough that the humans in charge of tracking it had to interrupt their own schedule and rush out a fix. The most recent full version, released for 2025, now places the pole closer to Siberia than it has ever been in the record, pushing into territory that earlier maps never had to describe. Now, who actually cares about a correction to an obscure magnetic model? Almost everyone, it turns out, without knowing it. Submarines navigating beneath the ocean and the ice, where satellite signals cannot reach, lean on the magnetic field to know their heading. Military and commercial aircraft carry the model in their systems, ships at sea use it, and the phone in your pocket uses it too. When your map app spins to show which way you are facing, it is reading a small magnetic sensor and correcting it against a model of the field so that the little arrow points to true north instead of magnetic north. That correction comes from this exact lineage of work. When the pole moves, that correction has to be updated, or every one of those systems slowly develops an error. There is even a charming concrete example of the field reshaping the built world. Airport runways are named with numbers based on their magnetic heading, and as the field has drifted, some airports have actually had to renumber and repaint their runways to keep the signs honest. The moving core reaches all the way up into the paint on a runway. Here is why I put the pole and the anomaly in the same story, rather than treating them as two separate curiosities. They are two faces of a single fact. The Earth's magnetic field is not a fixed, dependable backdrop. It is a living, shifting thing, generated by a flow of molten metal that rearranges itself on timescales we can now actually watch, and it is doing several dramatic things at once, right now, in our lifetimes. Over the South Atlantic, it is thinning and splitting. Over the Arctic, its pole is racing and then breaking. Both are the surface signs of a core in a period of visible change. And that raises the question everyone eventually asks when they learn all this, the question that launched 1,000 alarming headlines. If the field is weakening in one place and the pole is running in another, does that mean the whole thing is about to flip? Are we watching the beginning of a full magnetic reversal? To answer that honestly, we need to understand what a reversal actually is, and the truth is both stranger and, in one crucial way, far less cinematic than the movies would have you believe. Part 15. Does the needle ever flip for good? A magnetic reversal is exactly what it sounds like. The north and south magnetic poles trade places. Compass needles that once pointed to the Arctic would point to Antarctica instead, and stay that way. This is not a fringe theory or a doomsday fantasy. It is an ordinary, well-documented part of the planet's history, and we can prove it happened, over and over, by reading a record the Earth wrote for us at the bottom of the ocean. The record works like a tape recorder made of stone. Along the mid-ocean ridges where the seafloor is constantly being born, molten rock rises, cools and hardens. As it hardens, tiny magnetic minerals inside it line up with the Earth's field at that moment and freeze in place, locking in the direction of north like a compass needle set in concrete. New rock keeps forming and spreading outward on both sides of the ridge, so the seafloor becomes a slowly moving conveyor belt carrying a frozen history of the field. And when scientists mapped the magnetism of the ocean floor, they found stripes, alternating bands where the frozen field points one way, then the other, then back again. Those stripes are the fingerprints of reversals. The story of how we cracked that code is worth a moment, because it took decades and several stubborn scientists. In 1906, a French physicist named Bernard Brun noticed that certain volcanic rocks were magnetized in the direction opposite to the present field, the first real hint that north and south had once been swapped. In the 1920s, a Japanese researcher named Motonori Matuyama studied lava flows and argued, correctly and against heavy skepticism, that the field really had reversed in the geologically recent past. Their two names are now permanently attached to the boundary of the last reversal. But the case was not sealed until the 1960s, when scientists mapping the magnetism of the seafloor recognized that the alternating stripes matched the pattern you would expect if new crust was spreading outward from the ridges, while the field flipped back and forth, an insight now known as the Vine-Matthews-Morley hypothesis. That single idea helped confirm both seafloor spreading and magnetic reversals in one stroke. By carefully dating the stripes, and layering in shorter flickers within the longer intervals, events with names like the Jaramillo and the Olduvai, we learned that the field has completely flipped many times. There have been at least something like 183 reversals in the last 83 million years, which averages out to roughly one every 450,000 years. But that average hides wild irregularity. Sometimes the field holds steady for millions of years. Sometimes it flips several times in a much shorter span. There is no clock, there is no schedule. The last full reversal, the one called the Brunnis-Matuyama reversal, happened about 780,000 years ago. Now here is the single most important thing to understand about a reversal. The fact that quietly dismantles most of the doomsday versions of this story. During a reversal, the magnetic field does not switch off. It does not drop to zero and leave the planet naked for 1,000 years. What the ancient records show is that as the field flips, its strength drops substantially, perhaps down to something like 10% of normal, and its shape gets complicated. Instead of one clean north and one clean south, the field temporarily breaks into a messier pattern, with multiple poles scattered around the globe, several norths and several souths at once, before it eventually reorganizes itself into a simple field again, pointing the opposite way. So even at the depth of a reversal, there is still a field. It is weaker, it is tangled, it lets more radiation through, and it would absolutely cause the kinds of problems we have discussed for satellites and power grids and navigation. But it is not the total collapse of the shield. The planet does not go bare. And then there is the timescale, which is the other great deflator of panic. A reversal is not a Tuesday. It is not something that happens between breakfast and dinner, or even within a single human life. The best analyses of the last full reversal suggest the whole process, from the field starting to break down to a stable reversed field re-establishing itself, took something on the order of 22,000 to 30,000 years, with the most intense part of the transition happening within a narrower window of maybe 10,000 years. 10,000 years. That is longer than all of recorded human history. If the Earth's field began a full reversal today, no single person, no single generation, no single civilization as we understand the word, would live to see it finish. It would be a process unfolding across hundreds of human lifetimes. That is a very different thing from the sky falling, and it is exactly why the honest answer to is the field about to flip is so unsatisfying and so important to get right. Because the real answer is not yes, and it is not a simple no either. The real answer is that we genuinely cannot tell, and that not being able to tell is not the same as it being about to happen. Part 16. The Overdue Trap. You have almost certainly heard the phrase, "We are overdue for a magnetic reversal." It shows up in documentaries, in headlines, in the comment section of every video ever made about this topic, said with a knowing certainty, as if the Earth had a library book that was 3 days late. I want to take that phrase apart carefully, because it is the single most common thing people believe about this subject, and it is wrong in a way that is genuinely worth understanding. The overdue idea comes from a simple piece of arithmetic. If reversals happen on average every 450,000 years, and the last one was 780,000 years ago, then we are past the average, and therefore the reasoning goes, one is due. But that logic only works if reversals happen on a regular schedule, like buses, and they do not. The average is calculated across a process that is wildly, almost defiantly irregular. The gaps between reversals in the geological record range from a few thousand years to tens of millions of years. There is also a whole category of events that are not full reversals at all, and they are far more common. These are the excursions, the failed flips we met earlier through the Lashump event, where the field weakens dramatically, staggers, and then recovers its original polarity instead of finishing the switch. The record is dotted with them. Only a few thousand years before Lashump there was another one, sometimes called the Mono Lake excursion, and going further back the pattern repeats again and again. What that tells you is both important and steadying. The field dips toward collapse fairly often, in geological terms, and most of the time it climbs back rather than flipping. So a weakening, even a serious one, is not a reliable sign that a full reversal has begun. It might be the opening of a flip. It might just be the field doing the thing it has done countless times, sagging low and then standing back up. Both look identical at the start, and that is precisely the problem we are stuck with today. There have been long, calm stretches where the field held one polarity for an enormous span, and busy stretches where it flipped again and again. Taking the average of numbers that scattered and treating it as a due date is like noting that people have, on average, one testicle and one ovary, and concluding that the next person you meet will have one of each. The average is real. The schedule it implies is imaginary. 780,000 years since the last reversal is not alarming on its own. It sits comfortably inside the normal range of how long the field can go between flips. So the strong doomsday version, the it is overdue and therefore imminent version, does not survive contact with the actual statistics. But now I have to turn around and give the other side its due, because the fair-minded scientist does not stop at debunking the overreach. The field decline we are measuring is real, and it is not nothing. Some researchers have pointed out that if you take the current rate at which the dipole is weakening and simply extend it forward, the field would reach the kind of low values associated with a reversal or a major excursion in somewhere around a couple of thousand years. That sounds dramatic and it gets quoted a lot, but notice the load-bearing word in that sentence. If the current rate continues, and there is no guarantee it will, the field has weakened before and then recovered without flipping. The decline could slow, stall, or reverse itself next century. Projecting a straight line forward from the present is one of the oldest ways to fool yourself, because nature rarely travels in straight lines. So where does that leave us, honestly? Not overdue, because there is no schedule to be late for. Not imminent, because even a real reversal takes thousands of years to unfold, and the field is still strong. But not nothing either, because the decline is genuine. It is concentrated over the South Atlantic in a way tied to the structure of the Earth's interior, and it is happening fast enough, and strangely enough, to keep the best scientists in the field watching closely rather than dismissing it. The correct emotional response is not panic, and it is not a shrug, it is attention. And attention is exactly what turns this from a doomsday rumour into a real scientific story, because there is one place in the solar system that shows us in cold and final detail what the far end of losing your magnetic field actually looks like. It is the planet we are currently spending billions of dollars trying to reach. Part 17. The Dead World. Next door. Mars is often sold to us as a hopeful place, a second home, the next chapter of human exploration. I want to show you the other Mars for a moment, because it is the most honest teacher we have about why the thing under discussion tonight matters at the most fundamental level. Mars is what happens to a rocky planet when its magnetic shield dies. It is our own possible future, frozen 4 billion years in advance, sitting right next door for us to study. Mars was not always the cold red desert we know. Early in its history, it very likely had a churning molten core and a global magnetic field much like ours. We are not guessing about this. When spacecraft mapped the magnetism of the Martian surface, they found regions of ancient crust, especially in the southern highlands, that are still magnetized, still carrying the frozen imprint of a field that existed when that rock formed. Mars wrote itself the same kind of magnetic memory the Earth's seafloor did, and that memory tells us that once, long ago, the Martian dynamo was alive and the planet had a shield. We can even put dates and instruments to this. In 1997, a spacecraft called Mars Global Surveyor arrived at the planet and detected those bands of magnetized crust in the southern highlands, striped much like the Earth's sea floor, the fossil signature of a dynamo that has been dead for something like 4 billion years. Then, in 2013, NASA launched a mission named MAVEN for the specific purpose of watching Mars lose its air, and it caught the planet in the act. MAVEN measured the solar wind-peeling gas off the top of the Martian atmosphere at a rate on the order of 100 grams every second, and found that the loss jumps higher whenever a solar storm sweeps past. 100 grams a second sounds almost trivial until you multiply it by billions of years. Grain by grain, the sun carried an entire planet's sky off into space, and it's still carrying away what little remains, because there is no longer any shield to stop it. That is the slow-motion death our own field has been holding off since before there was life to appreciate it. There is a larger thought hiding inside all of this, one that reaches past our own planet entirely. If a magnetic field really is part of what lets a rocky world keep its air and its water long enough for life to take hold, then the search for life among the stars may quietly depend on it. When astronomers point their instruments at distant planets and ask whether any of them could be alive, one of the unspoken questions underneath is whether those worlds have a churning core and a shield of their own, or whether they are more like Mars, exposed and slowly bleeding out into space. Our field is not just a local convenience that makes compasses work. It may be one of the rarer and more valuable things a planet can have, and we happen to be standing on a world that has kept one running, almost without a break for most of its existence. And in that era, Mars appears to have had a thicker atmosphere, liquid water running across its surface, rivers, lakes, maybe seas. It looked, in the broadest terms, like a world where the story could have gone somewhere. Then the engine died. Mars is smaller than Earth, so its core cooled faster, and at some point the convection that powered its dynamo shut down. The magnetic field faded away, and once the shield was gone, the sun went to work. The same solar wind that our field deflects every day began to strike the top of the Martian atmosphere unopposed, and over hundreds of millions of years it stripped that atmosphere away into space, molecule by molecule. A spacecraft called MAVEN was sent specifically to measure this process, and it found the loss still happening today, the Martian air still bleeding away into the dark. As the atmosphere thinned, the pressure dropped. The planet could no longer hold liquid water at its surface, and the world dried out and froze into the desert we see now. The rivers became dry channels, the seas became dust. Mars did not explode or get hit by anything cataclysmic. It simply lost its magnetic field, and then it lost everything the field had been protecting. That is the real reason this subject deserves your attention, stripped of every exaggeration. The shield is not just about satellites and compass corrections and pretty auroras. On the longest timescale, the magnetic field is one of the things standing between a living blue water-covered world and a dead red one. It is part of the answer to why Earth kept its air and its oceans while its neighbour lost both. When scientists talk about searching for life on other planets, this is increasingly on the checklist. The question of whether a world has, or ever had, a magnetic field to keep its atmosphere from being blown away. A dynamo may be one of the quiet prerequisites for a planet staying alive long enough for anything interesting to happen on it. But I promised you honesty in both directions, so here is the essential caveat, and it matters. Earth is not about to become Mars, and a magnetic reversal would not turn us into Mars. The stripping of the Martian atmosphere took hundreds of millions of years, and it happened because the field went away completely and permanently. Our field is weakening in one region, not dying globally, and even a full reversal leaves a real field in place and lasts only thousands of years before recovering. The Mars comparison is not a forecast for next century. It is the far end game, the ultimate meaning of the shield, the reason the whole system is worth understanding rather than a prediction of doom. Mars tells us what the field is for. It does not tell us the field is failing on any timescale that should frighten a person alive today. And yet, sitting between the real science and the real reassurance, there is an entire industry of fear built on this subject. A whole ecosystem of claims that take these genuine facts and twist them into something they are not. If you have made it this far, you deserve to be able to tell the difference. So let me show you the stories people tell about the end of the shield and exactly where each one parts ways with the truth. Part 18. The stories we tell about the end of the shield. Whenever there is a real phenomenon that is genuinely a little frightening and genuinely not fully understood, a whole forest of stories grows up around it. The magnetic field is a perfect host for this because it is invisible, it is powerful, it is changing, and most people have never had it explained to them properly. So let us walk through the biggest stories one by one, and I will do for each of them what this channel always tries to do. Take it seriously enough to actually examine it, and then tell you honestly where the science lands. Start with the one many of you will remember, the 2012 apocalypse. For years leading up to that date, a story circulated that the ancient Maya calendar predicted the end of the world in December of 2012, and one popular flavour of that prediction was that the Earth's magnetic poles would suddenly flip and civilization would collapse. The date came and went, as you may have noticed, and nothing happened. The whole thing was built on a misreading of the Maya long count calendar, which was not predicting an apocalypse at all but simply rolling over to a new cycle, the way your car's odometer rolls over without the car exploding. There was never any physical mechanism behind the 2012 claim, no scientific basis for a sudden flip on a specific date, and the poles are not on a calendar anyway. That one is simply false, top to bottom. The next story is older and far more interesting, because a genuine scientific giant got attached to it. Back in the middle of the 20th century, a scholar named Charles Hapgood proposed an idea he called Earth crust displacement, the notion that the entire solid crust of the planet could suddenly slip, all at once, over the interior, sending continents lurching thousands of miles and causing global catastrophe. Hapgood's book on the subject even carried a foreword written by Albert Einstein, who found the idea intriguing enough to comment on, and that detail has kept the theory alive in popular culture for decades. Hapgood actually laid the idea out across more than one book, over the 1950s and after, and popular writers have kept it circulating ever since, because a sudden planet-wide catastrophe simply makes a better story than centimetres a year. But the physics is unforgiving. To make the entire rigid crust suddenly slide over the interior, you would have to overcome the enormous grip between the crust and the mantle beneath it, and rearrange how the planet's mass is balanced around its spin axis, and there is no known force that does either of those things on a human timescale, and no mark of such an event anywhere in the geological record. The continents do move, but at the pace of growing fingernails over millions of years, in the slow, well-documented choreography of plate tectonics. The magnetic pole is the thing that can travel quickly. The solid ground it travels over cannot. It gets tangled up with the magnetic story because people hear pole shift and picture the whole world physically tipping over. But here is the crucial distinction. The magnetic pole moving, which absolutely does happen, is not the same as the physical crust or the rotational axis of the planet lurching, which does not. The evidence from geology is overwhelming that the crust moves at the pace of plate tectonics, a few centimetres a year, about as fast as your fingernails grow, not in sudden catastrophic slips. Einstein was a physicist, not a geologist, and his curiosity about an idea in the 1950s is not evidence that the idea is right. The magnetic pole running to Siberia does not drag the continents with it. The ground under your feet is not going to lurch. Then there is the cover-up story, the claim that scientists or governments know a catastrophic reversal is imminent and are hiding it from the public to prevent panic. This one collapses the moment you look at how the information actually flows. The data on the weakening field is not hidden, it is published. The swarm satellite results are announced by the European Space Agency for anyone to read. The World Magnetic Model is a public document. The visualization of the growing anomaly was made and released by NASA's own visualization studio. If there were a secret, It would be the worst kept secret in the history of secrets, announced in press releases and posted online for free. The truth is almost the opposite of a cover-up. The scientists are practically waving their arms trying to get people to find this as fascinating as they do. And finally, the one that connects to an older legend, the idea that the South Atlantic anomaly is behind mysterious disappearances, that it is some kind of Bermuda Triangle in the sky swallowing planes and ships. This makes a certain intuitive sense if you squint. A weak spot in the field sounds spooky and vaguely dangerous. But the actual documented effects of the anomaly are on spacecraft electronics in orbit, hundreds of kilometers up, passing through the sagging edge of a radiation belt. It does not reach down and disable aircraft or ships at the surface, and there is no credible link between the anomaly and any pattern of surface disappearances. The real hazard is specific, and it is high above your head, not at sea level. So strip all of it away and notice what is left, because this is the part that matters. When you remove the false stories, you are not left with nothing. You're left with a set of facts dramatic enough that they do not need any embellishment. The field is weakening. The anomaly is real. It is growing, and it is splitting in two. The pole is running across the Arctic. Satellites are already taking damage, and nobody can fully explain the details or say for certain where it goes next. The truth is quieter than the apocalypse, but it is a great deal more interesting, because unlike the apocalypse, it is actually happening. And that leaves one last honest question, the practical one. If the weakening did keep going, if the anomaly did keep growing over the coming centuries, what would that actually mean for a world like ours? Not the movie version, the real one. Part 19. What a failing shield would actually do to you. Let us do the thought experiment cleanly, because it is the fairest way to size up the real risk. Suppose the current weakening is not a passing wobble. Suppose it continues, the anomaly intensifies and widens over the coming centuries, and the field slides toward the kind of low strength seen during an excursion. Not a total collapse, because we have established that does not happen, but a serious prolonged weakening. What actually goes wrong, and just as importantly, what does not? Start with what does not, because it clears away the Hollywood image. The atmosphere does not get stripped away. That is a hundreds of millions of years process that requires the field to vanish entirely and permanently, which is not what a weakening or even a reversal does. The oceans do not boil, the crust does not flip, gravity does not change, and the human body does not suddenly stop working because a compass points a different way. Life on Earth has lived through hundreds of reversals and countless excursions, including the near collapse at Lashom only 42,000 years ago, and our own species walked right through that one. Biologically, directly, a weaker field is not an extinction event for humans. The doomsday framing fails on the evidence. Now the part that is genuinely concerning, and it is concerning precisely because of who we have become. Everything that makes a weak field dangerous today runs through our technology. A prolonged weakening would mean more radiation reaching the altitudes where satellites fly. And we have more satellites up there than ever, with more launched every month. It would mean geomagnetic storms from the sun reaching farther and biting harder, and our power grids, our long pipelines, our undersea cables, our communication networks are all vulnerable to exactly that kind of induced electrical surge. The grid is the piece that should concern a modern person most, and the reason hides inside a component almost no one ever thinks about. The backbone of every large power network is the high-voltage transformer, and the biggest of these are not items you can pull off a shelf. They're custom-built, enormous, staggeringly expensive, and they often carry lead times of many months to more than a year to replace. A severe geomagnetic storm can force direct current into these transformers, heat them from within, and damage or outright destroy them. We already watched a storm collapse Quebec's grid in minutes, and we already know from the telegraph fires of the 1800s what induced currents do to a wired world. The scenario grid engineers genuinely lose sleep over is a Carrington-scale storm striking today's far more electrified, far more interconnected civilization, ruining many of those irreplaceable transformers at once, and leaving whole regions without dependable power not for hours but for far longer, while replacements are slowly manufactured. Now weaken the shield standing between that storm and the grid. You have not changed the physics of the storm at all. You have simply lowered the wall it has to clear. It would mean aurora appearing at low latitudes, which is beautiful, and it would also mean the radiation environment for aviation and for astronauts getting worse, and navigation systems that lean on the field needing constant correction. A weaker ozone layer and a rise in surface ultraviolet, the mechanism that is real from the Lasham story, would be a slow, genuine health and ecological pressure, not an instant catastrophe but a background cost that accumulates. There is also a quieter kind of casualty to consider, one that has nothing to do with electronics. A surprising number of animals navigate using the Earth's magnetic field. Migratory birds appear to sense it and lean on it to steer across whole continents. Sea turtles seem to read it to cross entire oceans and return, years later, to the very beaches where they hatched. Other creatures, from certain fish to some insects, appear to carry their own built-in compass. A field that weakens, shifts, and grows patchy does not only confuse our machines, it can scramble the invisible map that living things have trusted for millions of years, potentially nudging migrations off course in ways scientists are only beginning to study. It is one more reminder that the shield is not merely a barrier against radiation, it is also a signal woven through the whole living world, and when that signal wavers, creatures far beyond the reach of our technology may feel it too. The same weak spot that forces a telescope to close its eyes may also be tugging, gently and invisibly, at the instincts of a bird crossing the ocean far below it. Here is the sharp irony at the centre of all this, and it is the thing I most want you to take away. The humans who lived through the Lasham event, under a field that dropped to a few % of its strength, survived it. They had no satellites to lose, no power grid to burn out, no navigation systems to scramble, no global network of electronics for a radiation surge to corrupt. They looked up at strange auroras over the tropics, they endured a harsher sky, and they carried on. We would look up at the same strange auroras, and then we would watch our infrastructure struggle, because we have built our entire civilization on precisely the technologies a weak field threatens most. In a very real sense, a failing shield is more dangerous to us than it was to our ancestors, not because the physics got worse, but because we got more exposed. We wired the world in a way that assumes the shield stays strong. That is the honest weight of this story. Not extinction, not the end of the world, but a slow, expensive, disruptive pressure on the exact systems that modern life cannot function without, arriving on a planet that has quietly bet everything on those systems. It is a risk worth taking seriously without pretending it is the apocalypse, and that balance, real danger without doom, genuine mystery without fantasy, is exactly where I want to leave you, because it is the truest description of where the science actually stands. So let me bring the whole thing home and tell you what it means that you and I happen to be alive at the precise moment humanity finally learned how to watch this happen. Part 20. The first humans to watch it happen. Step all the way back and look at the shape of what we have covered, because when you see it whole, it is genuinely astonishing. Almost 3,000 kilometers beneath your feet, an ocean of liquid metal has been generating a magnetic shield for billions of years, the shield that lets this planet keep its air, its water, and its life. That shield is not steady. It is thinning, worldwide, by close to 9% since we started measuring, and the thinning is piled up over the South Atlantic into a growing weak spot where our own machines have to hide from the radiation that pours through. That weak spot is being shaped from far below by a buried continent-sized structure at the bottom of the mantle. It is growing by an area half the size of Europe in a decade. And now, for the first time in the observational record, it is splitting into two. Meanwhile, on the other side of the world, the very point of magnetic north has abandoned Canada and run most of the way to Siberia, sped up, then braked harder than ever recorded, all of it driven by the same restless engine at the centre of the Earth. And here is the thing that makes our particular moment unique in the whole human story. Every generation before us lived under this same shifting field and could not see it. They had compasses and guesses. They had rock records they did not know how to read. The field could have been doing all of this above their heads and they would never have known. We are the first. We are the first human beings with 3 satellites in formation, mapping the shield continuously, with models precise enough to catch a weak spot dividing in real time, with a visualization of the anomaly crawling across a single decade. For all of history, the changing of the Earth's magnetic field was a process locked in stone, readable only long after the fact. We turned it into something we can watch live. That is a genuinely new power, and it came with a genuinely new and uncomfortable kind of knowledge. Because watching it live does not mean understanding it fully. This is the honest centre of the whole story, the thing I have circled back to in every part, and I am not going to pretend our way out of it at the end. We can see the shield thinning. We can see the anomaly splitting. We can see the pole running. What we cannot yet do is tell you which story we are in. In one story, this is the planet breathing, a slow, ordinary fluctuation of a field that has weakened and recovered many times, and in a century or two the numbers drift back and the alarm fades into a footnote. In the other story, this is the quiet opening of something rare, the first frames of an excursion, or a reversal that will take thousands of years to play out but has in some sense already begun. The data we have right now is consistent with both. That is not a comfortable place to end, but it is the true one, and I would rather leave you with the real uncertainty than a fake answer. So watch the things that will actually tell us, because there are specific signals and now you know how to read them. Watch whether the anomaly's new second cell, the one pulling toward Africa, keeps growing, because that split is the newest and strangest behaviour in the record. Watch the World Magnetic Model, whose next scheduled revision comes at the end of this decade, and notice if the pole forces another emergency update before then. Watch that single global number, the rate of the dipole's decline, because if it holds steady it means one thing, and if it accelerates it means another. And watch the sun, because the next great solar storm to strike a thinned shield over a weakened South Atlantic will teach us, in a single event, things no model has been able to settle. These are not abstractions anymore. They are the specific places where the answer will show itself first. We have always believed the ground beneath us was the one thing we could count on, the fixed foundation under everything else. But the field that ground generates has never been fixed, and now we get to watch it move. The shield that has guarded every living thing that has ever existed on this planet is developing a hole over the Southern Ocean and tearing that hole slowly in two, in full view of our instruments, for reasons no one has completely explained. Maybe it fills back in, maybe it does not. And that is the question I cannot stop turning over, the one I will leave sitting with you tonight. If the field is already this weak, already splitting, already outrunning the models built by the smartest people we have, then how exactly are we supposed to tell the difference between the planet breathing and the beginning of the real thing until the day it is no longer a question we get to ask from a safe distance, but something already happening to us all?